Hello students, very good afternoon. This is Mayur S. More, your chemistry tutor. I welcome you all to JEE Chemistry, session number 2 for chemical equilibrium. As you all know, we started this chapter in last session. And what did we see in last session? We saw that how the chemical reactions are, some of their types, and we see the types of chemical reactions. Then we saw how can you determine the rate of a particular reaction. Okay, today we're gonna take this forward. Today we're gonna take this forward where we're gonna see what chemical equilibrium actually is. In the last lecture, I just gave you a bit a hint of chemical equilibrium. You might say that you started a chemical equilibrium chapter, but you haven't mentioned anything about it. See, for to understand chemical equilibrium, you need to understand some of the other facts of the chemical reaction first, and then we can dive into the chemical equilibrium. Okay, then you will understand much more aspects of it. Okay, so chalo, let's begin on that note. I welcome you all to JEE Chemistry. Let's begin. So, chemical equilibrium. Yeah, what is it? See, the state of the reversible chemical reaction. State of the reversible chemical reaction at which, see, it is that state of the reversible reaction at which the rate of a forward reaction becomes equal to the rate of backward reaction. See, you can see here A reacts with B to give you C plus D. So when you're A reacting with B to give you C plus D, that is what? That's a forward reaction. Okay. And what does RF stands for? RF stands for rate of forward reaction. Okay. Similarly, C reacts with D to give you A plus B back. So here your products are reacting to give you a reactant back. Okay, so it's a backward reaction. That is why we call this as backward reaction, and rate of this reaction is equal to RB. So RB is equal to rate of backward reaction. RF is equal to rate of forward reaction. Now what is chemical equilibrium? It is that state. It is that state when rate of forward reaction is equal to rate of backward. So it is that state where rate of forward reaction is exactly equal to rate of backward reaction. They are not. So this does not mean that reaction is not moving anywhere. Reaction is moving. Okay. Reaction, it is like, let me give you a simple example. Suppose there are two floors. Okay. There are two floors in a building. And suppose the first floor has around like 300 people sitting there. Okay, so this is the first floor and this is the second. Okay, suppose the first floor initially has 300 people. There are 300 people here. Okay, now what happens after 1 hour? That in the second floor, let's see, 300 people in the first, and there are 0 people. Actually there are 0 people in the second. Okay, now as the slowly things progresses, what happens? There are 180 people in the first floor and 120 people in a second floor. Okay, now at this stage what happens? That with each passing minute, 10 people are moving from first floor to second floor, and 10 people are moving from second floor to first floor, which keeps this and this constant. So that does not mean that concentration of your reactant or concentration of your product remains constant. They are changing. They are changing. Okay, they are changing. But the rate of forward reaction, that means now you understood what is rate, right? We have discussed about in the last lecture. The rate with which A and B are reacting to give you C and D, that rate is equal to the rate with which C and D are reacting to give you A plus B. Basically, rate of forward reaction is exactly equal to rate of backward reaction. And that state in a reversible reaction, where both these rates are equal is called as chemical equilibrium. Okay, I will tell you with the help of graph also, but that on the next slide, because you might not, I do not have a space here. Okay, so as I was saying, the state of the reversible chemical reaction at which the state of the reversible chemical reaction at which the properties of the system, like temperature, concentration, color, density, don't undergo any change with time at the given set of condition. It's said to be in a chemical equilibrium condition. That means, see, whenever, see, how can you observe the equilibrium? See, there are some criterias. In this case, I told you the criteria was number of people in the each floor. Okay. Here, what are the criteria? How can you monitor the given chemical reaction? The chemical reaction can be monitored by measuring the properties. What are those properties? Like temperature, concentration, pressure, color, density. Okay. So what I'm saying, that the state of reversible chemical reaction at which the measurable properties such as the temperature, concentration, color, density, etc., they don't undergo any change with a time at the given set of condition. And then only you can call this as to be in a chemical equilibrium condition. Okay. Now, one more thing. You need to understand one more thing. See, as the reaction progresses, see, rate of any reaction is directly proportional to the concentration of the reactants. Whatever reactants you have, the rate of particular reaction will be dependent on the concentration of those reactants. As the reaction progresses, the concentration of reactant decreases. So as the concentration decreases, the rate of reaction would obviously decrease. So which rate would decrease? The rate of forward reaction. Okay. So that is what I was saying. The rate of a forward reaction decreases as the concentration of product increases. Concentration of product increases means what? Concentration of reactant is decreasing. That is why concentration of product is increasing. That is obvious, no? Because reactants is getting converted into product, right? So if the concentration of product is increasing, that means concentration of reactant is decreasing. If the concentration of reactant is decreasing, it is obvious that the rate of that forward reaction would obviously decrease. Okay? So now what will happen? As the rate of forward reaction decrease, as the concentration of product was increasing, up they go, concentration of product has increased. Now what will happen? Now the rate of backward reaction will start increasing. Why? Because the concentration of product is increasing now, right? So now rate of backward reaction also start increasing. Okay. When the initially rate of forward reaction was very high, eventually it got decreased. Initially rate of backward reaction was very less. As the concentration of product was increasing, the rate of backward reaction was also increasing. So it is like that, rate of forward reaction is decreasing, rate of backward reaction is increasing, and eventually the state will come when both the reaction rates are same. That is called as the state of equilibrium. But one more thing, this happens only in a reversible chemical reaction. Okay. Now let me make you understand this with the help of diagram. Okay. Look at this. This is your time. This is time. And this is what? Our rate. On the y-axis you have rate. On the x-axis you have. So, see, this was the rate of a backward reaction. Sorry, forward reaction. And this is where the rate of backward reaction. Because backward reaction was not existing, right? Initially, backward reaction wasn't existing. Why it wasn't existing? Because there was no product. If there is no product, why there would be a backward reaction? And if there is no backward reaction, why there would be a rate of backward reaction? But reactant was initially always there. The rate of forward reaction is very high initially. Slowly what happened? It starts declining. It starts declining like this. It starts becoming a flat. And as this reaction rate decreases, at the same time, the product is forming more and more, because of which the rate of product, sorry, the concentration of product will increase. With that, obviously the rate of backward reaction will also increase, and that is why it eventually starts increasing like this. Eventually it also becomes flat. So let me tell you, this is the case. See here. Here it starts becoming equal. So this is where, let me use you another color. This is where chemical equilibrium, this is where chemical equilibrium is attained. This is where chemical equilibrium is attained. Okay. Now let me name those. See, this is your rate of forward reaction, or I should write this as RF. What is this? This is your rate of backward reaction, right? Or I should rather write this as RB. Okay, and this is RF. So as the concentration of reactant is decreasing, the rate of forward reaction is declining. As the concentration of product is increasing, rate of backward reaction will increase, and eventually the state will come where both the rates of forward and backward reactions are exactly same, and that is when the equilibrium, chemical equilibrium, is said to be attained. Okay, so that is what the whole point about chemical equilibrium is all about. Okay, now let's understand some of the characteristics of your chemical equilibrium. What are those? See, at equilibrium state, rate of forward reaction is exactly equal to rate of backward reaction. That we have discussed already, right? Now, at this state of equilibrium, forward and backward reaction proceeds with the same speed. That means whatever speed your forward reaction is moving, same speed your backward reaction is moving. It is just like the saying that both of them are having the same rate. There's one and the same statement. Okay, now the stage of the reversible reaction at which the concentration of reactants and products do not change with time is called as equilibrium state. That means whatever reactant concentration you have at equilibrium, suppose the change in concentration of reactant is from 5 moles to 2 moles, and increasing concentration for product is 0 moles to 2 moles, then there would not be a substantial change in the concentration change of a reactant or a, if it is a 2 moles of reactant, it would stay 2 moles. If it's a 5 moles of product, it will stay 5 moles of product, just like that. क्योंकि जितना भी रिएक्टेंट प्रोडक्ट में कन्वर्ट हो रहा है उतना ही प्रोडक्ट रिएक्टेंट में कन्वर्ट हो रहा है. यू आर गेटिंग माय पॉइंट. जितना रिएक्टेंट प्रोडक्ट में कन्वर्ट हो रहा है उतना ही प्रोडक्ट रिएक्टेंट में कन्वर्ट हो रहा है. तो उस वजह से because of that there is no as such change in their concentration. Their concentration do not change with time. That is called as a equilibrium state. That's a second characteristics of your equilibrium state. Thirdly, equilibrium state is dynamic in nature. You need to understand this point really well. Equilibrium state is dynamic in nature. That means you can shift the equilibrium state. See, if the given reaction attains the chemical equilibrium, it will always attain the chemical equilibrium. But it can be changed with the temperature. If you have a different temperature, you will have a different value of a chemical equilibrium. That is the only thing which can change it. So that is why I'm saying equilibrium state is dynamic. What is meant by dynamic? Something which can move. Static means what? Something which is constant or stationary is called as static. Something which can change is called as dynamic. Okay. So equilibrium state is dynamic in nature. And lastly, the main characteristic that you need to understand that the reaction does not stop. Reaction does not stop, but both the opposing reactions, that is forward reaction as well as backward reaction, both the opposing reactions are going on continuously with same speed. They are going on with the same speed. Reaction as such does not stop. Okay, so that is what all about the chemical equilibrium. I hope you must have understood it pretty well. Okay, if you have any doubt, you can ask me in the comment section. Okay, so moving ahead, what are the some other characteristics? See, chemical equilibrium, as I already said, is dynamic in nature. Means, what is the meaning of that? Although although reaction appears to be stopped. Now you might say, see, whatever number of reactant, whatever concentration of reactant which is getting converted into product, same amount of product is getting converted into reactant. So as an outsider, it appears that reaction has stopped, right? As an outsider, it appears that reaction has stopped. But reaction is not stopped. It is actually happening. It actually happening, but only thing is that actually it takes place in both the direction with the same speed. Reaction is happening with both directions the same speed. Yeah. Now, secondly, to obtain equilibrium, if any of the reactant or product is in a gaseous state, then the reaction should be carried out in a closed vessel. We have talked about this in the last session also when we were discussing reversible reaction and irreversible reaction. Chemical equilibrium can only be attained in a reversible reaction. And for you to attain reversible reaction, if any of the reactant or product is in the gaseous phase while the course of the reaction is happening, then you should be always carrying out in a closed vessel. Or else what will happen? Some of the gas might get evaporated. Some of the gas might get escaped, and then there will be no product or reactant for it to cause a chemical equilibrium. Okay. Thirdly, at a given temperature, and pressure of equilibrium, the properties like concentration, color, density remain constant. So as I told you earlier, that at given temperature and pressure, equilibrium equilibrium reaction system will have a same concentration, color, density, that and density also. All of them will remain constant. However, if you change the temperature and pressure, the value of concentration, all of that might change. Okay, so it is a temperature specific system. And lastly, in order to prevent escape of products, equilibrium is reached only in a closed vessels, in a reversible reaction. Understand that point very well. Your reaction should be reversible for it to attain chemical equilibrium. Secondly, you need to make sure that reaction happens in a closed vessel because it cannot be attained in an open vessel at all. Okay, sure. Moving ahead, I hope you must have understood it pretty well. If you got any doubt, you can ask me in the comment section. Okay, so moving ahead now, taking forward characteristics. Yeah. So, in a reversible chemical reaction, why I'm putting this, you need to understand this point really, really well. In a reversible chemical reaction, the equilibrium state can be attained in a lesser time. In a reversible chemical reaction, the equilibrium state can be attained in a lesser time by the use of positive catalyst. Now, firstly, you need to understand what is meant by catalyst. The catalyst is any substance which alters the rate of reaction. Now, see, generally people uses the term for a catalyst that any substance which increases the rate of reaction. Now, it is not that. Yeah, you can say as a general that catalyst is any substance which increases the rate of reaction. Why? See, generally, catalyst is any substance which increases the, catalyst is that substance which alters the rate of reaction. It might increase the rate of reaction or it might decrease the rate of reaction. So the proper word or the original word is it alters the rate of a reaction. Now, if your catalyst is positive, it would increase the rate of reaction. If your catalyst is negative, it would decrease the rate of reaction. But the thing is that the catalyst which is a negative catalyst, there is no term as such as a negative catalyst, because negative catalyst is called as a poison. They are called as catalytic poisoning, because you only think in this way. Why you carry out a particular reaction? Because you want a product, right? You carry every reaction to obtain a product. That product might be useful for different purposes, right? That is why you are performing a reaction. So why do you want a substance that would decrease the rate of reaction which is giving you a product? Okay, you will always want a substance which would rather increase the rate of reaction so that you can obtain the product faster, because that product is useful for you now. And that is why the people generally uses the word that any substance which increases the rate of reaction is called as a catalyst, but in reality that is not. Okay, so I told you both the side of this. Now let's understood how catalyst or positive catalyst can increase the rate of reaction. Yeah, so see, again, I need to make you understand that through a chart. Okay. Suppose here your A plus B is reacting. Okay. This is your, suppose this is your time. Okay. And this is heat. I would rather say delta H. Heat of reaction. Okay. Now, so this is where your heat is. So it is going like this. Okay. It is coming down here to give you C plus D. What is C plus D? That is your product. What is A plus B? That is your reactant. Right? Now, so this is the level of your heat for A plus B. From there, it needs to reach to this point. What is this? That is called as transition state. Okay. So you can see here, this much is the amount of energy. This is called as delta EA. What is delta EA? Delta EA is called as energy of activation. It is called as energy of activation. It is a minimum energy. It is a minimum energy required to be supplied to every reactant for it to attain a product. Every reactant needs to provide a certain minimum energy for it to react and to produce a product. That minimum energy is called as energy of activation. Okay, so this is a transition state. In transition state is a state where your reactant is transitioning from reactant to product, or you can say it is a state exactly in between the reactant and product. Okay, so your reaction can only happen when your reactant reaches to transition state, and from there it comes down in the energy to form a product. Okay, now, so for this to happen, your reactant needs to reach to the transition state, and it should be obtained or increase, sorry, it should be absorbing some amount of energy. Okay, now what happens with the catalyst? So this reaction, let me write this color. This reaction that you're seeing right now is uncatalyzed reaction. It is uncatalyzed reaction. There is no catalyst provided here. Okay? Now let's this red color reaction. Now if you put a catalyst here, what will happen? Now this reaction will happen. It will go here, and from there it will come down. See, this is the transition state now. Now this transition state, this is TS1, this is TS2. This is for what? This is catalyzed reaction. Now see, catalyst doesn't do any magic here. This red one is what? This red one is your catalyzed reaction. Now you took same reactant. You keep every condition exactly same. But now what happened? For this red wala reaction to happen, it takes less time. Why less time? Because catalyst provides the alternate path. Catalyst provides the alternate path to a reactant for reaction, because of which your reactant requires less energy of activation. Your reactant requires less energy of activation. And for it to reach here, it needs to absorb less energy and also less time. Because of this, red wala reaction will happen at the faster rate. And that is how catalyst actually can increase the rate of a reaction. Got it? So, as I was saying, in a reversible chemical reaction, the equilibrium state can be attained in a lesser time by the use of positive catalyst. A catalyst doesn't change the equilibrium state. See, if suppose this reaction A plus B is giving you C plus D, if this reaction is reversible, then catalyst, it's not that catalyst will increase the rate of forward reaction only. No, it will increase the rate of backward reaction also. So catalyst basically increases. Get my point very clearly. So catalyst basically increases the rate of both the reactions. When it increases the rate of both the reaction, what will happen? The rate of forward reaction and backward reaction will eventually come closer to each other, and eventually they will become same. When they will become same, we say that equilibrium state has been achieved. So basically catalyst helps in attaining the equilibrium faster. Catalyst helps in attaining the equilibrium faster. It does not specifically increase the rate of either forward or backward reaction. It increases the rate of both reactions simultaneously and thereby making equilibrium to be attained fast. Okay. So as I was saying, a catalyst doesn't change the equilibrium state because it increases the rate of both forward and backward reaction simultaneously by changing the path of a reaction, and it helps in attaining equilibrium rapidly. That is what catalyst does. Okay, mark this point very clearly. Next, now there are only some last notes that you need to understand. See, whenever question doesn't ask about direction, suppose in exam they don't ask you about whether it's a forward direction or backward direction, then you understand, then we consider, we take into consideration forward direction only. Because why you're doing a reaction at the first place? You are mixing A plus B to obtain C plus D. You don't want A plus B back, right? Because if you really want A plus B back, then why would you mix them at the first place? You would not, right? You want C plus D, that is why you are mixing A plus B. ओके, नहीं तो क्या इस तरह, ये तो ऐसा होगा ना कि भाई हमको कुछ काम नहीं है, चलो ए प्लस बी को मिक्स करते हैं, इक्विलिब्रियम अचीव करते हैं. नो, इट्स नॉट लाइक दैट. यू वांट सी प्लस डी, राइट? So whenever a question being asked and if there is no mentioning of a direction, then understand that it's about forward direction only. Last point. In a reversible reaction, if forward reaction is exothermic, in any reversible reaction, if forward reaction is exothermic, then the backward reaction will always be endothermic and vice versa. If the forward reaction is exothermic, then understand that backward reaction will obviously endothermic. And vice versa means if the forward reaction is endothermic, then the backward reaction will be exothermic. It will always be the case. Okay? Sure. Moving ahead. Now, what are some of the types of equilibria? Now you understood what is chemical equilibria thoroughly. Okay. Now let's understand the types of equilibria. There are two types of equilibria. One is physical equilibria. So this one is physical equilibria. Another is what? Another is chemical equilibria. We have already seen what chemical equilibria. Now let's understand what is physical equilibria. See, if in a system only physical state, what is meant by physical state? Whether it's in a solid state, liquid state, gaseous state, whatever that state, if there is an equilibrium between that state, then it is called as physical equilibrium. Okay. So if in a system only physical state or only physical phase is changed and then the equilibrium is established, that is, there is no chemical change. For example, when your ice melts, ice is what? Water. When your ice melts to give you water, do you observe any chemical change? No, there is no change. See, what is meant by chemical change? Whenever there is a change in a composition, it is called as a chemical change. So when you melt a solid to get your liquid water, there is no change in a chemical composition of it. So this is not a chemical change. It is what? Physical change. When you vaporize a liquid water to a gas, and then there's an equilibrium between gaseous state and liquid state. That is the physical equilibrium again. There is, even if you have a vapor, it's still water. Even if you have a liquid water, it is still water. Even if you have ice, it is still water. So these are only physical state that are changing, not chemical composition. And that is why all of those are called as physical states. Okay? Yeah. So if in a system only physical phase is changed and then the equilibrium is established between the two phases, then it is called as physical equilibrium. For example, fusion of ice. When your ice, this is ice, okay, you provide a some heat to it. What do you obtain? You obtain a liquid water. Okay. Now suppose here, if you keep the temperature constant, if your delta T is 0, if your delta T is 0 here, that means there is no change in concentration, and you have kept a pressure also constant. Delta P is also 0, delta T is also 0. Then there is a development of a equilibrium. So this is your ice, this is water. So what will happen? Some of the ice will get melted to give you liquid, and then some of the liquid will start getting converted into ice. It will start freezing. Then the time will come when the amount of molecules of ice which are getting melted and amount of molecules of water which are getting frozen, the rate of those both the processes will be same. And then we said the physical equilibrium has been attained. Okay, so the fusion of ice, okay, evaporation of water, that means boiling of water again, dissolution of salts, and absorption of gases and liquid, all of these can attain physical equilibrium under given conditions. Okay, the very first, what are the types of common physical equilibrium? The very first, liquid and vapor equilibrium. In a closed vessel, the vapors above the liquid are in equilibrium with the water at a given temperature. See, this is the vessel. It has the water like this. This is your water. Okay. And you are heating it. You are heating it. Okay. And it is closed now. So what will happen? It will form the vapors, right? These are your vapors. So amount of water which is getting converted to the vapors and amount of vapors coming back to the water, their rates are same. When that is same, the physical equilibrium is said to attain. So this can only happen in a closed vessel. This is a closed vessel. If you keep this vessel open, what will happen? The water will get converted into vapors and those vapor will be lost. And then you would not have the vapors which can come back to the water. And therefore, there would not be any equilibrium as such. That is why to attain the equilibrium, you need to have a vapor. And to keep the vapor there, you need to have a closed vessel there. Okay. So that's a liquid vapor equilibrium. Now, solid liquid equilibrium. Solid liquid equilibrium, I already told you. Ice is solid. This is liquid water. Okay. So this equilibrium can be established only at melting point of solid. So this can only happen at 0 degrees Celsius. And you need to make sure the temperature of the system where ice and water, both of them are in equilibrium, the temperature of this whole system stays at 0 degrees Celsius. Temperature doesn't change. If the temperature stays at 0 degrees Celsius, then there would be equilibrium. That means whatever ice you have taken, some of the ice will getting melted into water and same amount of water will getting frozen into the ice. Basically, there would not be any conversion of ice into water on technical ground. So I mean to say this equilibrium can be established only at melting point of solid. And melting point of ice is what? It's a 0 degrees Celsius, as we all know that, right? So as I was saying, at this stage, solid liquid phase exists simultaneously in equilibrium. As solid liquid and gas phase will exist simultaneously in a liquid vapor equilibrium. Similarly, in a solid liquid equilibrium, solid and liquid phases exist simultaneously. Okay, so moving ahead. The next equilibrium that we have is solute solvent. See, saturated solution equilibrium. What is mean by saturated solution equilibrium? See, when you put a salt into water, initially some of the salt start getting converted into dissolve. Some of the salts is getting dissolved into water. Okay, it gets dissolved. you put 1 spoon of salt, 2 spoon of salt, 3 spoon of salt, it will keep on dissolving until the stage will come, where the solution becomes saturated. What is mean by saturated solution? It is a solution where you cannot dissolve the salt anymore. It is a state of a solution where you cannot dissolve any salt anymore in it. Okay. So basically, saturated solution equilibrium, what happens that the rate of dissolution of solids in liquid is equal to the rate of crystallization of solid from the solution. That means what? See, you see your water. Okay. Initially, what happens is that you put some of the salts into it. Okay. After some time, what happens is that whole salt has got dissolved into it. Now there is no salt into it. Okay? It has got dissolved. So you can't see it, right? When you dissolve a sugar or salt into this, you can't see it. Okay. But after some time, or I would rather say on standing, what happens that some of the salts can be seen appearing at the bottom. These salts which you have dissolved into your liquid solution to obtain a solution, after some time on standing, this starts, you can see them appearing at the bottom. Now what is that? That's a crystallization. This process is called as crystallization. Whatever salt you have dissolved, that is now crystallizing back to solid state. Initially what happened? Some of the solid state substance, or I would say solid, was getting dissolved into liquid solvent to form a solution. When saturation came, this some of the dissolved solid started coming back into solid state. That is called as crystallization. And whenever your solution is saturated, then what will happen? The rate of this dissolution and rate of this crystallization becomes exactly same. Rate of dissolution and rate of crystallization becomes same. That is called as solute solvent equilibria. Okay. That is what I was saying. What is the main point here? This can be only observed if the temperature is constant. Because see, some of the salts, when they dissolve into water, there can be more solid dissolved into water if you increase the temperature. Why? Because whenever those salts are dissolving into water, they absorb the amount of heat. So that the process of dissolution is endothermic. So when the process is endothermic, if you're providing heat to it, it will happen to the more extent. Okay. So in that case, if you increase the temperature, the more solid will be getting dissolved. And in that case, this crystallization will not happen. And therefore, there will not be any equilibrium as such, or equilibrium might be attained later on. Okay. Similarly, if for the some of the solids, when they are getting dissolved into water, they release the amount of heat. So when you increase the temperature of that system, then the crystallization process will immediately start happening. Because when you increase, system is already releasing the heat. So when you are providing heat to it, it will start going into the backward direction. Okay? That is why for this equilibria, you need to keep the temperature constant. So you can see here NaI is getting dissolved into water to get you Na plus and I minus. After some time, what happens? Na plus I minus starts combining with each other to give you NaI. But if you keep the temperature constant here, that means delta T is 0, then equilibrium can be seen to be achieved. Okay, so one more point concerned with this particular example. This NaI wala example, above example is of solubility of a sparingly soluble salt, which only depends on temperature. See, there are many sparingly soluble salt. What is mean by sparingly soluble salt? Sparingly soluble salts are the salts which are soluble to very, very, very less extent. For example, NaI, AgI, AgCl, these are sparingly, or I can say PbSO4, these are sparingly soluble salt. They are soluble in a water to the very less extent. So whatever you have understood right now, it is applicable for only those. It is not applicable for the solids which are easily soluble in water, or the solids which are more soluble in water. For example, salt, sugar, it is not applicable to those. Okay, I hope you must have understood pretty well. Moving ahead. Now, next, gas plus solvent. See, saturated solution equilibrium. What is this? See, in such equilibriums, solvents is saturated with respect to gas. That means the rate of entering of a gas molecules in a solvent is equal to rate of escaping of gas molecules from solvent. Again, this phenomenon can be observed in a closed container at definite temperature. For example, you might know, you must have drunk this cold drinks, right? You must have consumed Coca-Cola, Pepsi, and all of those. So, do you observe that as soon as you open the cork, as soon as you open their cork, the gas immediately comes out, right? The bubbles comes out. What is that? That's the dissolved CO2 in that. So these are aerated drinks. These drinks are called as aerated drinks. Okay. Or I can tell you the one more term is used for them is carbonated. Carbonated water. It is carbonated water. Okay. So yeah. So what is happening in them? So they already have a dissolved CO2 in them. Okay, but that is under pressure. As soon as you remove the cork, what happens? As soon as you remove the cork, the pressure is released. Because of that released pressure, the dissolved gas in that liquid comes out. Because the solubility of any gas in a given solvent is directly proportional to the pressure above it. If the pressure is decreased, the solubility of gas will be less. When the solubility is less, that means it comes out like that. Okay, so whenever you have a gas dissolved in that, see, these are the gas molecules. Some of the molecules are getting dissolved, some of the molecules are coming out, and there is an equilibrium. Since it is sealed, right, it is already sealed, so the amount of gaseous molecule amount of gaseous molecule which are getting dissolved into that solvent and amount of gaseous molecule which are coming out of it, both of them, the rate of both of them is exactly same, and that is called as your gas solvent equilibrium. Okay, sure. Moving ahead with this, types of equilibrium. So, as I was saying, the solubilities of gases in liquid is a function of pressure of gas over the liquid. So, if this is your liquid and these are your gaseous molecules which have been dissolved into it, okay, and this is your cork over it. So, pressure. So, whatever pressure you have, the solubility of amount of gas which has been dissolved here is directly proportional to the pressure of this gas over the liquid. इसका मतलब लिक्विड के ऊपर से गैस जो भी प्रेशर उसके ऊपर exert कर रहा है, the amount of gas which can be dissolved in that will be proportional to the pressure of that gas over the liquid. Okay, and that is nothing but the manifestation of Henry's law. It is nothing but the Henry's law. It can be applied on such system that states the mass of a gas dissolved in a given mass of a solvent. The mass of a gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent. whatever pressure these gaseous molecules are exerting on this liquid surface, the amount of gas which can be dissolved in that is proportional to that pressure at given temperature. What is Cg? In other words, Cg is directly proportional to Pg. What is Cg? Cg is the solubility of a gas in the mole per liter, obviously. Pg is the pressure of that gas, and K is what? Henry's constant. So basically this is the Henry's constant. It states that amount of gas that can be dissolved in a given solvent is directly proportional to the pressure exerted by those gas molecules on the surface of that liquid. That is what it ultimately says. Okay. And lastly, the one should not compare it with liquid vapor equilibrium. Liquid vapor equilibria is completely different than this. Okay. There is no connection between that and this. Okay. So moving ahead with this. Now, we had seen the physical equilibria already. Now let's see chemical equilibria. Well, we know what chemical equilibria is, right? Here I am just here to tell you some of the examples of it. So we already know when chemical change occur in a reversible reaction, that is reactants converted into product and products are also converted into reactant under similar conditions of pressure and temperature. Okay, the reaction is said to be in a equilibrium. Now, just to see, yeah. So H2 reacts with I2 to give you 2HI. This all reaction is also reversible, formation of HI. Similarly, SO2 reacts with Cl2 to give you SO2Cl2, sulfuryl chloride. That is a reversible reaction. PCl3 reacts with Cl2 to give you PCl5, reversible reaction. And this is formation of ammonia. This is also Haber's process. This is also a reversible reaction. So these are some of the examples of reversible reaction. Okay. Yeah. The next point, or the last point of today's lecture, the law of mass action. What is law of mass action? Law of mass action or law of chemical equilibrium. Law of mass action or law of chemical equilibrium. See, the law of mass action is given by, these are the name of two scientists, Goldberg and Wig. Okay, let's forget it. So according to them, at a given temperature, rate of a reaction is proportional. According to them, at a given temperature, rate of reaction is proportional to product of active masses. Rate of a given reaction at a given temperature, rate of any reaction is proportional to the product of active masses of reactants. At that instant, raised to a power which are numerically equal to the number of their respective molecules in the stoichiometric equation describing the reaction. Now you would not understand this immediately. So let me give you an example. Suppose you have A moles of A reacting with B moles of B to give you C moles of C plus D moles of D. Whereas this small A, B, C, D, what are those? A, B, C and D. These are stoichiometric coefficient. They are called as stoichiometric coefficient. Now you might say, sir, what is this stoichiometric coefficient? See, look at this reaction. Here 2 moles of ammonia are decomposing to give you 1 mole of nitrogen, 3 moles of hydrogen. So what is this 2 moles? What is this 2 and 3? This 2 and 3 are called as stoichiometric coefficient. Similarly, you are getting 1 mole of H2 is reacting with 1 mole of I2 to give you 2 moles of HI. What is this 2? Stoichiometric coefficient. Basically, it is the number of molecules. It is the number of molecules in that balanced chemical equation. Okay. So yeah, A moles of A reacts with B moles of B to give you C moles of C plus D moles of D. So what is forward reaction? Where A and B are reacting to give you C and B. This is forward reaction. And what is this? Backward reaction. Okay. So as far as rate of reaction is concerned here, what is the rate of forward reaction? As per the Goldberg and Wake, the rate of forward reaction into bracket RF is directly proportional to the concentration of A and concentration of B. With, what are they saying? At a given temperature, rate of reaction is directly proportional. Directly proportional, this is a symbol, right? Directly proportional to the product of active mass. So this is the product of active masses of reactant, right? How many reactants are there? A and B, two are there, right? So it is the product of active masses of reactants at that instant, raised to a power which are numerically equal to the number of their respective molecules in the stoichiometric equation describing the reaction. So if you look at here, what are the stoichiometric coefficient of A and B? For A, it's A, small a. For capital B is small. So that is rate of forward reaction. That is what is called as law of mass action. So basically RF, that means rate of forward reaction is equal to KF. What is K? It's a constant.